go ahead and get started. So we're going to start with the last page from class V, which is just using trig identities to simplify trigonometric expressions. And so I will tell you, there's kind of there's two main, maybe I guess three main things I think about doing when I'm given some complicated trigonometric expression and asked to simplify it. Thing one, write everything in terms of sines and cosines, meaning cotangent of x, I'm going to replace with cosine x over sine x. Tangent of x is sine x over cosine x. Secant of x is 1 over cosine x. Cosecant of x is 1 over sine x. So that's kind of my first thought process is I'm usually going to write everything in terms of sines and cosines because it's easier to deal with. The second thing we look out for is the Pythagorean trig identity. That sine squared theta plus cosine squared theta equals 1. So those are the two things I'm thinking about when I'm trying to simplify this expression. So if I have cosine of x times cotangent of x plus tangent of x, I'm going to rewrite the inside part here as cotangent of x is going to be cosine of x divided by sine of x. And tangent of x is going to be sine of x divided by cosine of x. Now, I would like to be able to actually write things as one fraction, but I need a common denominator. So that's what I'm going to do next. I'm going to do the common denominator. Right, this is cosine of x times cosine x over sine of x times cosine x over cosine x plus sine x over cosine x times sine x over sine x. So now these two expressions will have the same denominator, which is sine of x times cosine of x. So let's simplify that a little bit. I'm going to write this as cosine of x times cosine x times cosine x is cosine squared x. Sine x times sine x is sine squared x. And then we're going to be dividing by the denominator sine of x times cosine of x. What can I do now? Say it one more time. Exactly, yeah. Cosine squared x plus sine squared x is equal to 1. So this is exactly cosine of x times 1 over sine of x times cosine of x. What else can I do? Well, I can cancel a cosine. Or you could write this if you wanted to as cosine over sine times cosine, but I'm just going to go straight to, well, that cosine is really, it's cosine of x over 1, and I can definitely cancel that cosine there and that cosine there. So I'm left with 1 over sine of x, which I really should write as cosecant of x. And now we've simplified the expression down to one trigonometric term. Questions about anything we've done? Yeah. Hey.
I mean, once again, I don't want to sound dumb.
No.
I want to try to figure it out at night and morning. But for tan x, why did you send sine over
Cosine? So that's what tangent's defined to be equal to. If you look back to like when we were talking about the triangle and the unit circle. So that's our angle there, and the opposite, this side was y, and the side was x, and the side was 1. Right, sine of theta is y over 1. Cosine, or opposite of hypotenuse. Cosine of theta is adjacent of hypotenuse. And what's tangent of theta? Which side over which side?
opposite over?
Right, so you can tell opposite over adjacent. So tangent of theta is y over x. But look, y over x is exactly sine of theta over cosine of theta. And that's so I will say it's kind of one of the go-to identities. Like if I'm thinking about things I can do to manipulate an expression, replacing tangent of theta with sine of theta over cosine theta is like one of the first things I try. And that in addition to cotangent theta being replaced with cosine theta over sine theta. So those are kind of the two of the really big ones. So this, remember, so this triangle is coming from the unit circle
Not triangle, the step before.
right here.
Yeah.
So the other thing we have, so in this right triangle, in here, I'm going to write the Pythagorean theorem that x squared.
I see.
But I think everyone wants to. I'm going to show it to everybody, just so everyone can see. X squared plus y squared equals 1 squared. I'm exactly answering that question. What happened to sine squared and cosine squared? So x squared plus y squared equals 1 squared, but x is cosine. So that's cosine squared theta. Y is sine. That's sine squared theta. And it's equal to 1, or 1 squared, which is 1. So when you see cosine squared plus sine squared, that's automatically, oh, that's going to equal 1. We're going to replace it with 1. And I usually call that the world's most famous trigonometry, because it's kind of like the most famous one. Everyone, that if someone said, what's one trigonometry you know, that's the one. Oh yeah, cosine squared x plus sine squared x equals 1. So those are the two main things. Olivia.
Why are you multiplying cosine over cosine by the cosine of the sine?
Well, so when I was adding these two fractions together, we can only add fractions if we have a common denominator. So I had to get a common denominator, so I multiplied this one by cosine over cosine, and this one by sine over sine, so that I would have a common denominator of sine times cosine.
Oh.
Other questions? Good questions. All right, let's look at the next one. So here I see sine of x divided by secant of x times cosecant of x minus cotangent of x. And again, I'm going to go back to my default kind of step of I'm going to write everything in terms of sine and cosine. So the numerator is just sine of x. Secant of x is 1 over cosine of x. Cosecant of x is 1 over sine of x. And cotangent of x is cosine of x divided by sine of x.
You could also think of it as in x and y.
I really would prefer not to, actually, because the problem with that is you're right. You could if you really want to, you could write y equals sine, and secant would be 1 over x and 1 over y and x over y, and then you could manipulate that. But I feel like you're more likely to make an error if you kind of forget what the things mean, or if you aren't writing what they mean. So in the numerator, I have sine of x, and here I have the fraction 1 over cosine x times sine x. And here I have the fraction cosine x divided by sine of x. And once again, I'm in a situation where I would like to add or subtract two fractions together, but they don't have the same denominator. So I need a common denominator. So what am I going to multiply cosine x over sine x by so that I have a common denominator? Yeah, cosine x over cosine x. Right? I need another cosine in the denominator so that this fraction and this fraction will have the same denominator. All right, so let's see what we've got now. Got sine of x divided by 1 over cosine x sine x minus cosine squared x over cosine x sine x. And I really should have put those fractions together in that step. I feel like I can write essentially the same step again. I've got sine of x divided by 1 minus cosine squared x all over cosine x times sine of x. Okay. So now, what's 1 minus cosine squared of x equal to? Well, we're going to go back to our trig identity here. Cosine squared theta plus sine squared theta equals 1. Then if I subtract sine squared from both sides, I've got that cosine squared theta equals 1 minus sine squared theta. That's actually not what I wanted, right? I did the wrong one. That's okay. That's an important one to know. If instead we subtract cosine squared from both sides, we're going to have sine squared theta equals 1 minus cosine squared theta. So these are two alternate versions of the Pythagorean trigonometry. And they're both nice to know. So that 1 minus cosine squared x there, I'm going to replace with a sine squared x. I'm going to have sine of x divided by, I could have flipped and multiplied at this point, but I didn't. Sine squared x over cosine x times sine of x. Now let's flip and multiply. So I've got sine of x times the reciprocal of this. Cosine x times sine of x divided by sine squared of x. What can I cancel? I can cancel a sign there and a sign there. I can also cancel a sign there and the other sign there. I'm left with just cosine of x. Yeah.
Okay. For the like the third step in the process.
Right here.
No, the second one.
Here.
How did you get sine in the denominator of the bottom left
Here.
fraction? Yes.
So in the previous step, secant became 1 over cosine. Cosecant became 1 over sine. And those are multiplied together.
Oh, so you just, okay.
Right. So when you multiply fractions, it's always top times top, bottom times bottom.
Yeah, okay.
So that's what I did. I did 1 times 1, which is 1, and cosine times sine, which is cosine times sine. All right, let me throw one more example at you. Which, like this one's actually less complicated. That's all right though. Let's say we have 1 minus cosine x times cosecant x plus cosecant x. And I feel like you could go in one of two directions to start off with. Erica.
So there's like a popular piece in the whole, and my first question is, do you use like
So one way to go would be to first FOIL it out. Right, you could totally FOIL this out. So you've got 1 times cosecant. You've got 1 times cotangent. I really should draw the little arrow. I always draw the little arrows. And then I've got minus cosine times cosecant. That's cosine x times cosecant x. And then minus cosine times cotangent. That's probably the better thing to do first. The other option first would be to rewrite cosecant as 1 over sine and cotangent as cosine over sine. But I think this is a better first
We
step.
do 1 minus cosine, replace it with sine.
So be careful. That's a common error people make. 1 minus cosine squared x is equal to sine squared x. But I've seen many students over the years want to say that 1 minus cosine is equal to sine. It's not the case. You got to have the squares. So 1 minus cosine squared is equal to sine squared. And now I would replace all the things with sines and cosines, meaning I'm going to rewrite cosecant of x as 1 over sine of x. And I'm going to rewrite cotangent of x as cosine x over sine of x. And I'm going to rewrite cosecant of x as 1 over sine of x. I'm going to rewrite cotangent of x as cosine x over sine of x. And something cancels right off the bat. What can I cancel here? Well, I've got a cosine over sine and I've got a cosine over sine. Right, this is cosine x over 1 times 1 over sine of x, and that's the same as cosine x over sine of x. So this term here cancels with this entire term here. And then I'm left with things that have a common denominator. I have a 1 over sine of x minus cosine times cosine is cosine squared x over sine of x. I really should have just written that as one entire fraction with the common denominator sine of x. The numerator is 1 minus cosine squared x, which I can replace with what? Sine, right? So this is going to be sine squared x over sine of x. And sine times sine divided by sine, one of the signs cancels, right? You can even write, I don't think you have to write it out, but this is really sine x times sine x over sine x. One of those cancels.
Is this like the way to solve this problem, or is it just?
It's one way,
Okay.
right?
Then-
So with, and that's kind of true for a lot of these trig simplification problems, is there's usually more than one way to do it. I'm trying to show you the way I think is the easiest, but there are other paths you could certainly take.
The way to check if you're right.
It's not, there's not really an easy way to check if you're right. Yeah, the way you, so if I was trying to check this and I didn't have any other tools, what I might try doing honestly is graphing each of the things in Desmos. If you graph y equals sine of x and you graph y equals 1 minus cosine x and cosine x plus cotangent x, the graph should look very similar. They might be a little bit different because there's some domain issues, but essentially they should be the same. But that's not really a good answer to your question. There is not a good answer to your question.
Oh, so when you're asking us to simplify to a single term, would that ever be like a fraction or like 1 over cosine or?
So if you got 1 over cosine, I would prefer your answer was what? Oh, you're so close. Secant. So here's the thing. So the way I remember the reciprocal ones is cosine, its reciprocal doesn't have a co. And sine, since it doesn't have a co, its reciprocal does have a co. So the reciprocal of sine is cosecant, the reciprocal of cosine is secant. And of course, tangent and cotangent go together. They both have tangent in the word. But yeah, I would, yes. So if you had 1 over cosine, a better way of writing that is it's just a secant of x.
Yeah, okay.
Sometimes the single term you simplify things to is 1. Sometimes 1 is an answer. All right, let's move on to W. Or the French say W, which is double V. And actually, let's actually start with the second page here. I feel like the second page is more what we want to be doing. So let's go look over at page 2 and talk about how sine of A plus B does not equal sine of A plus sine of B. And in a similar way, I also want you to know cosine of A plus B does not equal cosine of A plus cosine of B. Let's look at an example of that. Okay, so here's a quick example. Sine of 30 degrees plus 60 degrees. 30 degrees plus 60 degrees is definitely 90 degrees. And if you're thinking about 90 degrees, if you're looking at unit circle, 90 degrees is right there. And the point on the circle is 0, 1. So sine is which? Is it 0 or is it 1? 1. So remember, they're alphabetical. X before y, cosine before sine. The x coordinates the cosine, the y coordinates the sine. So sine of 90 degrees is going to be positive 1. On the other hand, sine of 30 degrees plus sine of 60 degrees. Well, sine of 30 degrees is 1/2. Sine of 60 degrees is the square root of 3 divided by 2. And I'm pretty sure that's not 1. Right, it's 1 plus the square root of 3 divided by 2, which certainly isn't 2 over 2. And if you plug it into a calculator, you'll see it's approximately 1.36, which is not 1. So I really, really, really want to emphasize when you're taking sine of an angle plus another angle, you can't just break it up into sine of the first angle plus sine of the second angle. On the other hand, here is the formula that's actually true, which is right below, which I'm going to show you here. Sine of 30 degrees plus 60 degrees is sine of 30 degrees times cosine of 60 degrees plus cosine of 30 degrees times sine of 60 degrees. Let's see that that's actually true. So sine of 30 degrees is 1/2. Cosine of 60 degrees is also 1/2. Cosine of 30 degrees is root 3 over 2. Sine of 60 degrees is root 3 over 2. 1/2 times 1/2 is 1/4. Square root of 3 over 2 times the square root of 3 over 2 is, well, square root of 3 times square root of 3 is 3. 2 times 2 is 4. And 1/4 plus 3/4 is 1, which is exactly what sine of 90 degrees should equal. So this is the angle sum formula for sine. The sine of A plus B is equal to sine of A times cosine B plus cosine A times sine of B. And there's also a formula for cosine. Cosine of A plus B is equal to cosine A times cosine B minus sine A times sine B. These are the angle sum formulas. There is also one for tangent. You don't really need to know it, because if anyone ever asked you to do it for tangent, I would just tell you to do it for sine and for cosine and then divide them. Do sine of the thing divided by cosine of the thing. But you could, there is a tangent one you could learn if you wanted to. I barely memorized it because I've seen it so many times, but like it's not a formula you need to ever know, I think, personally. I will also point out there are angle difference formulas. So sine of A plus B is this formula. Sine of A minus B is sine of A times cosine B minus cosine A times sine B. And the cosine of A minus B is cosine A cosine B plus sine A sine B. So for this formula for the sine function, the sine, S-I-G-N, stays the same. And for the cosine function, the sine changes. Sine same, cosine change. I don't know. It works for me. Okay, let's go back to the question, Erica. Well, we're definitely going to do an example where we use a difference formula, but I would agree most of the time we're using the sum formula. It's kind of the more used formula for sure. In fact, you can always use it instead of the difference, but there are a couple examples where we like to use the difference. So the reason I want to talk about that first, so then we can go back and see these double angle identities. Because now we can view these double angle identities through the lens of, oh, well, it's just the angle sum formula. If you look at sine of 2 theta, it's really just sine of theta plus theta. And I'm thinking of my theta as A and my other theta as B. So sine of A plus B is sine of A times cosine of B plus cosine of A times sine of B. Where theta is the A and the B. But look, those are the same. That's sine of theta times cosine theta. That's sine of theta times cosine theta. And if you take something and add it to itself, you have twice it. Right? 5 plus 5 is 10, but 5 plus 5 is 2 times 5. Sine theta times cosine theta plus sine theta times cosine theta is 2 times sine theta times cosine theta. Just like the formula says it is.
The original 2 is for the whole.
Say that one more time.
The 2 is for the whole, not just the sine.
That 2 is multiple. It's 2 times sine times cosine. So, I mean, yes, it applies to the whole, but there's no distributing of it because it's all multiplication. And then in a similar way, cosine of theta plus theta is cosine theta times cosine theta minus sine theta times sine theta, which is cosine squared theta minus sine squared theta. The thing I also want to point out is that it is not the case that sine of 2 theta does not equal 2 times sine of theta. And cosine of 2 theta does not equal 2 times cosine theta. Some examples of that. Let's let theta be the angle 30 degrees. sine of 2 times 30 degrees is sine of 60 degrees, which is root 3 over 2. On the other hand, 2 times sine of 30 degrees is 2 times, let's see, sine of 30 degrees is 1/2. That's 1. Those aren't the same. So I really want to emphasize, oh yeah, sine of 2 times 30 and 2 times sine of 30, not. The kind of not great part about this formula is that you can't really do a lot with it. At least not a lot of meaningful stuff with it. What I mean by this is I don't ever really use this formula to evaluate a trig function. But I'm not going to use this to find sine of 2 times 45 degrees because I already know that sine of 90 degrees is 1. So this formula isn't particularly useful for evaluating new angles, but it is useful for, well, it's useful really like in Calc 1 and Calc 2 when you're trying to do some derivatives or some anti-derivatives and you need to use this formula for everything. So later on, you're going to see that sine 2 theta equals 2 sine theta cosine theta is something you want to use when you're like, oh, I don't want to deal with this. I'm going to rewrite it like this. Same thing goes for cosine 2 theta. There's going to be times in your future where you don't want to deal with that, and it's going to be better to look at it like that. I know that's not helpful now, like why are we doing this, but that's what we've got. So one kind of question we can ask is if cosine is equal to negative 5/13, and we know that sine of theta is negative, find cosine of 2 theta. So I know that cosine theta is equal to negative 5/13. I'm going to draw myself a triangle, a right triangle, where the adjacent side is 5. I'm going to ignore the negative, and the hypotenuse is 13. And what's the third side of this triangle? Well, I know that 5 squared plus a squared equals 13 squared. A squared is going to be 169 minus 25, which is 144. So a is going to be the square root of 144, which is 12. Maybe a is not the best name for that side because it's not the adjacent, but I just picked a because it was a letter. I could have picked O. I could have picked X. So now we know the three sides of this triangle, 5, 12, and 13. And I want to find cosine of 2 theta, which is equal to cosine squared theta minus sine squared theta. Okay, well, we can find both these things. We already know what cosine theta is. It's negative 5/13. They told us. So it's going to be negative 5/13 squared. And what's sine of theta in this triangle? It is 12/13, but they told us that sine of theta was negative. So it's actually going to be negative 12/13 squared. Now, it doesn't really matter that it's negative or positive in this problem because we're squaring it either way. So we're going to get, let's see, 5 squared is 25 over 13 squared is 169 minus negative 12 squared is 144 over 169. And then 25 minus 144 is negative 119 over 169. Before we ask this next question on the same page here, I want to ask you all to show me on your fingers. If we know that cosine theta is negative 5/13 and sine theta is negative, what quadrant is theta in? Yeah, quadrant 3, because sine is negative and cosine is negative. So we know we're in quadrant 3. What we're going to ask now is what quadrant is 2 theta in? And we can't know without doing more work. So, right, if you know that if the first angle is in quadrant 3, it's between 180 and 270 degrees. If you double it, it's between 360 and 540 degrees, which is either going to be in quadrant 1 or in quadrant 2. But the way you really answer the question, what quadrant is an angle in, is by figuring out the positive or negativeness of sine and cosine. So if you know that sine is negative and cosine is negative, boom, you're in quadrant 3. If you know that sine of 2 theta is something and cosine of 2 theta is negative, well, We already know if cosine of 2 theta is negative, we're either in quadrant 2 or quadrant 3. We should figure out what's going on with sine of 2 theta to figure out which quadrant we're in.
Wait, why do we need to figure out which quadrant?
Well, because I'm asking an additional question.
Oh.
Right, because I'm asking what quadrant is 2 theta in.
That's the problem, like,
So the 20 degrees of cosine 20 degrees are the functions of.
Oh, so whoa. It's not 20 degrees, it's 2 theta.
Oh, 2 theta.
Yeah, so we don't actually know what angle, we don't know what the angle is. It's just a made up, like, here's an angle and cosine of it is negative 5/13. So let's find sine of 2 theta, which is going to equal 2 times sine of theta times cosine theta. And luckily, we've already found both those things. Sine of theta we know is negative 12/13. Cosine of theta we know is negative 5/13. If you multiply this all together, negative 5 times negative 12 is positive 60. So you get 2 times 60 over 169. And then 2 times 60 over 169 is 120 over 169. And then we could totally answer the question, what quadrant is 2 theta in? Well, cosine is negative, sine is positive, so what quadrant do we have to be in? Quadrant 2. Here's another easy question to answer at this stage. What's tangent of 2 theta? Well, this is where I would use the fact that tangent of an angle is equal to sine of the angle divided by cosine of the angle. That's going to be sine of 2 theta divided by cosine of 2 theta. Sine is 120 over 169. Cosine is negative 119 over 169. What cancels right away? What's the only thing that could cancel? The 169s, right? Because that when you flip a multiply, you're going to get 169 in the bottom, 169 in the top. And that's a common thing that happens, right? When you find sine and cosine, most of the time they have the same denominator. And so then when you divide them by each other, those denominators just cancel out. You get 120 over negative 119. I write the negative sign up front. That would be tangent of 2 theta. All right, back to page 2. Oh, question.
I don't know when we're gonna be like doing this for this class, but can you remind me how you would find theta in this situation?
I wouldn't, like, not that I wouldn't remind you. I wouldn't ask you to find theta in this situation. But if you were trying to find the angle, you would have to use a calculator. And you would find the inverse cosine of negative 5/13.
Okay.
Which we haven't talked about inverse trig functions yet.
how'd you get quadrant 2 for that?
So the way I got quadrant 2 was by observing that cosine was negative and sine was positive. And we know that, right, if we're talking all students take calculus here, the only quadrant where sine is positive for quadrant 1 and 2, the only quadrant where cosine is negative are quadrants 2 and 3. Oh, it's got to be this one where sine is positive and cosine is negative. No problem. So this angle sum formula can be used to evaluate sine and cosine and tangent, but we're not using for tangent, of some new angles. Some angles that aren't pi over 3 or pi over 4 or pi over 6, but a sum of them. So let's start with sine of 7 pi over 12. You could, if you wanted to, write this in degrees. 7 pi over 12 is 105 degrees. I'm going to show you kind of how to do this both ways. So when you're trying to take something like this and write it using the angle sum formula, the first step is to write the angle as a sum of two angles that we know how to deal with. So what are two angles that add the 105 degrees that we know how to find sine or cosine of? There's multiple answers. Well, there's one answer at least. The one answer I can think of is 60 degrees and 45 degrees. Those add to 105, and they definitely we know how to deal with. Now, let's say we didn't convert this. Let's say we were stuck with radians instead. There is a process I've used which always works, which is that if you're going to break 7 pi over 12 up into two angles that we know how to deal with, don't worry about trying to figure out what they are. Worry about trying to break this up into two angles that both reduce. Meaning find two numbers that add up to 7 that both reduce when you put them over 12. Let's see, 1 and 6 don't work because 1 never works. You can't reduce 1 over something. 2 and 5 over 12 doesn't reduce. 3 and 4, those both reduce. So I'm going to write this as 3 pi over 12 plus 4 pi over 12. And then I'm going to reduce those fractions. I'm going to write that as sine of 3 pi over 12 is pi over 4. 4 pi over 12 is pi over 3. Oh, look, it's the same thing we already said. That's sine of 45 degrees plus 60 degrees. Just in radians instead of degrees. It's totally fine to convert it to radians. It's to degrees. It's totally fine to not. I like not because I can always figure out how to add together to make it reduce. So then I'm going to use the formula. This is going to be sine of pi over 4 times cosine of the other angle plus, and then you switch it, right? Instead of having sine of pi over 4, you have cosine of pi over 4. Instead of having cosine of pi over 3, you have sine of pi over 3. Sine of pi over 4 is root 2 over 2. Cosine of pi over 3 is 1/2. Cosine of pi over 4 is also root 2 over 2. And if I know that cosine of pi over 3 is 1/2, I know that sine of pi over 3 is the other value that goes 1/2, which is root 3 over 2. And then we do like to add these together because here's the thing, these answers always come out looking essentially the same. Meaning it's always going to look like, well, let's see, root 2 times 1 is root 2 over 4, and root 2 times root 3 is the square root of 6 over 4. And then I'm going to write this as one fraction, square root of 2 plus square root of 6, all divided by 4. And for these angle sum formulas where it's something like 30 degrees plus 45 degrees, 60 degrees plus 45 degrees, or something like that, your answers are always going to look like this, meaning it's always going to be something positive or negative root 2 plus or minus root 6, all divided by 4. Every time. I know you guys are like, but yeah, every time we do something like this, it's always going to look like that. Let's look at the second example. And then we'll stop for some questions. So 165 degrees. There's probably at least a couple ways we could add to 165 degrees with angles we know. I'm thinking either 30 degrees and 135 degrees. Those are both angles we know. 135 degrees has a reference angle of 45 degrees. Or we could do 45 and 120. I usually like to do 45 and whatever's left over. I find it easiest to do it that way. So I'm going to write this as cosine of 45 degrees plus 120 degrees.
You should advise subtracting from that.
Well, so what would I subtract to make 165?
If it came to that.
I generally would advise adding to get to the thing instead of subtracting. I only subtract if I have to usually. Like for example, if we were to do sine of 15 degrees, then, oh, I'm going to say 45 degrees minus 30 degrees gets me 15 degrees. So this is going to be cosine of 45 degrees times cosine of 120 degrees minus sine of 45 degrees times sine of 120 degrees. Cosine of 45 degrees is the square root of 2 over 2. Cosine of 120 degrees. Well, 120 degrees is in quadrant 2 where cosine is negative. The reference angle is 60 degrees. We know cosine of 60 degrees is 1/2. So cosine of 120 degrees is negative 1/2. Minus Sine of 45 degrees is root 2 over 2. Sine of 120 degrees, well, again, reference angle 60, we're in quadrant 2. Sine of 120 should be root 3 over 2, and it should be positive root 3 over 2 because we're in quadrant 2. So multiplying this out, I have root 2 times negative 1. So negative root 2 over 4 minus root 2 times root 3 is root 6 over 4. And then writing this as one fraction, it is negative root 2 minus root 6 all over 4. Again, a plus or minus root 6 plus or minus root 2 all over 4. All of these answers are going to look like that. One thing specifically to be careful about when they're both negative is don't accidentally put that negative out in front of the fraction. So I just want to specify here, if you write it like this, it's actually not the same. Because when the negative is out front, it should distribute to each of the terms on top. And that would be a negative root 2 plus a root 6. So if you want to write it this way, when you're distributing, when you're factoring out the negative sign, you actually have to make that a plus. You don't need to do that, but I'm just pointing out if you put the negative out front, it's different than not.
Can you remind me why cosine of 120 degrees is negative 1/2? Okay, sorry, I know the relation to the reference angle, like why does that make it just a negative?
Well, so if we look back, right, if you think about what quadrant we're in, cosine of 120 degrees is a little bigger than 90. So we're over here in quadrant 2. And in quadrant 2, you can either think of, right, all students take calculus, sine is positive, cosine is negative, but you can also think cosine is the x-coordinate on the unit circle. And in quadrant 2, the x-coordinate is definitely negative because we've gone over to the left side of things. Those are two ways we could think about why cosine is negative there.
Okay.
Does that answer your question?
Yeah, and then I remember you mentioned like the reference angle,
Mhm.
bit, like yeah, you're talking about like how cosine of 60 is 1/2.
Mm-hmm.
My question was like, how does that relate? So like, would you just know like so do you just put a negative in front of the reference angle?
So I'm putting a negative in front of the value. So I'm saying I know that cosine of 60 degrees is positive 1/2 because either the triangle or the unit circle. And then if I'm trying to find cosine of 120 degrees, I know it's going to have the same value, but it might have a different sign. And it does. It's going to be negative because 120 degrees is in quadrant 2. On the other hand, if we were asked to find, say, cosine of 300 degrees, the reference angle is still 60 degrees because it's 60 degrees away from 360. But now the angle is in quadrant 4, where cosine is positive. So cosine of 300 degrees would be positive 1/2. But all I'm doing is I'm saying I'm going to use the reference angle to find the value, and then I'm using the quadrant to determine whether it's positive or negative.
Yeah, okay.
And then we have some, let's see, yeah, fine. We got enough time. I want to do a couple more examples of those, but let's work through these two examples, which I feel like we've already had homework questions about. And now we're kind of late to the game here. Finding trig values for hyperextended angles work the same way. You just find the quadrant. So if we want to find secant of 59 pi over 6, what we're really going to do is we're just trying to figure out what quadrant that angle is in. So let me ask you all. If my angle is 59 pi over 6, which I know is a lot of revolutions, and it's almost 10 pi. Like a 60 pi over 6 would be 10 pi. What's my reference angle? Pi over 6, right? So right off the bat, we can say, well, I know I'm dealing with secant of pi over 6. I never know what that is because I can't remember secant for the life of me. And I know that cosine of pi over 6 is 1/2. Nope, it's not. Root 3 over 2. Sorry about that. So I know that secant of pi over 6 is the reciprocal, which is 2 over root 3. And then I suppose I might rationalize it because I'm not going to be lazy about it like I would normally be. Now that's not necessarily my answer, but I know so here's what I know right now. I know that my answer to secant of 59 pi over 6 is either positive 2 root 3 over 3 or negative 2 root 3 over 3. I just have to figure out what quadrant my angle is in. Okay, there's a lot of ways you can attack this. I think, I don't know. So one way to do it is just to keep subtracting off multiples of 2 pi until you get an angle that's between 0 and 2 pi. So you could take 59 pi over 6 and subtract off 2 pi. There's 2 pi, 12 pi over 6, and get 47 pi over 6. That's still pretty big. I'm going to do it again and subtract off 2 pi. I'm going to get 35 pi over 6. Let's do it again. It seems a little tedious. I mean, welcome to math, right? It's not always tedious. It's just sometimes tedious. So do it one more time. And now look, I finally got an angle I recognize. 11 pi over 6. What quadrant is 11 pi over 6 in? Definitely in quadrant 4. So that's kind of the longer way of doing it. The easier, the way that requires a little bit of, I don't know, intuition or seeing a thing is what I said in the beginning. 59 pi over 6 is almost how much? Almost 10 whole pi. And 10 whole pi is how many revolutions around the circle? 5 revolutions. But we didn't quite get that 5th revolution. So we went 1, 2, 3, 4, and then we didn't quite make the 5th one. Oh, we're almost definitely in quadrant 4. Right? We were just pi over 6 short of 4 or 5 full revolutions. So that's in this case, a slightly easier way of seeing maybe what it is. I don't know if it's easier or just feels like there's less math to do. In either event, our angle's in quadrant 4, meaning cosine is positive or negative, which means secant is positive or negative. Whoa. If cosine is positive, secant is definitely also positive, because reciprocal things always have the same sign. You take the reciprocal of a number, you haven't made it all of a sudden negative for some reason. So secant and cosine always have the same sign. So our answer is going to be that secant of 59 pi over 6 is indeed positive 2 root 3 over 3. Do you need to write the positive? No. Do I like to write it to emphasize I know what I'm doing? Yes. Here is the next question that I think is a little easier. Oh, Erica. Well, no, I was subtracting 2 pi. Well, because I needed a common denominator, right? I can only subtract fractions that have the same denominator. So what I did without showing my work was I said 2 pi was the same as 12 pi over 6 by multiplying by 6 over 6. So 2 pi here over 1 times 6 over 6 is 12 pi over 6. So when I said I was subtracting 2 pi, I immediately converted it to 12 pi over 6 and then started subtracting away. Here's one that's, I feel like, less terrible. 99 pi. I know it's a lot of pi. It's too much pi for Thanksgiving. Okay. How many? So let me just ask it this way. 1 pi is half a revolution. 2 pi is a full revolution. 3 pi, halfway again, 4 pi, full. So if I do 99 pi, am I going to end up having done full revolution or a half revolution at the end? A half, right? If I do an odd number of pi, I'm always going to end up over here. So anytime you have an odd amount of pi, you end up there. Anytime you have an even amount of pi, we end up over there. So if I said my angle was 1,000 pi, you'd be like, oh, well, I'm back at where I started at the point 1, 0. If I said 1,000,001 pi, like, oh, well, I'm on the other side. So I've done an odd amount of pi. Erica.
So was the first one even because the reference angle pi was 6?
Well, so when you say even, well, this one was positive because we ended up in a quadrant, right? This angle was in quadrant 4, and it wasn't a whole amount of pi at all, right? This was some fractional amount of pi, 59 pi over 6. that was almost 60 pi over 6, which is 10 pi, which is 5 full revolutions. Here we actually have 49 revolutions plus half a revolution, right? This is 99 pi is 98 pi plus 1 pi. And that 98 pi is 49 revolutions. So I did 49 revolutions and then another half a revolution. So I ended up over here. Okay, what's the coordinate over there? Thank you, -1, 0. And secant is the reciprocal of which function? Cosine. And so cosine of 99 pi is -1, which means secant of 99 pi is 1 over -1, which is -1. Oh, sorry. Normally I would just say it's -1, but I was trying to show it there. So secant of 99 pi is 1 over -1, which is -1. I'm sure I could say more, but I also know it's 10:51. Technically, I'm supposed to stop saying things, so I'll stop there.